Okay, this is 3.2, number 39, and this is a doozy. And we see problems like this once in a while that you have to kind of do a lot of different algebraic techniques to get. This is an interesting one. So it says this is the function, this is a piecewise function, f of x equals 3 minus x when x is less than 1, and f of x equals ax squared plus bx when x is greater than or equal to 1, where a and b are constants. If the function is continuous for all x, what is the relationship between a and b? Well, if it's, remember, and we did this at the end of chapter 2, what value of a and b will make this continuous at x equals 1? So he just said that we know that if it's continuous, the vertical positions have got to be the same. In other words, it's got to connect. All right, so this is okay because this is just a line. And this is okay, it's a quadratic. So these are differentiable over their whole domains. There's no, like I say, there's no issues. Oh, well, they're continuous. Let's not talk about the differentiability yet. They're continuous and differentiable over their domains. There's no problem except for at the juncture point. Do they connect? If it connects, it's continuous. If it doesn't connect, it's not. And the only way it can connect is if the vertical positions at exactly x equals 1 are the same. So we set this vertical position to that vertical position. For x equals 1, we put the 1's in, and this is the relationship. So 3 minus 1 equals a times 1 squared plus b times 1. So 2 equals a plus b. So, all right, a plus b equals 2. That's the way they must be related in order for the function to be continuous. Okay, now letter B, and I didn't state it over here, but letter B, okay, find the unique values for a and b that will make f both continuous and differentiable. So we're assuming now that it's continuous. So that means over here at x equals 1, these have got to have the same height. So 3 minus 1 is 2. So we could say that f of 1 must be 2, and we also know that a plus b is 2. So we have these facts here that we've got from the a part to assure continuity. So in order for it to be differentiable, and for all x, and we know, like I said, that this is differentiable for all x and this is differentiable for all x. There are none of those, like I say, cusp, corners, vertical tangents, or discontinuities in any of these functions. So we just have to concern ourselves with these points and make sure the left derivative is equal to right derivative. So we're going to try to find values of a and b that will make that happen. So let's do the left-hand derivative and see what that's going to give us. So again, I use my same f of a plus h minus f of a. In this case, a is going to be 1 because that's our juncture point, 1. That's where they connect. So that's what I'm looking for. Everything else is okay. Now here, f of x plus h, if h is approaching 0 from the negative direction, I add a negative to 1, I'm going to be to the left of 1. All right? So if I'm going to be to the left of 1, I'm using this function here, 3 minus x. And we already asserted what minus f of 1, f of a, f of 1, but we already asserted that f of 1 must be equal to 2 in order for it to be continuous. See, we're assuming it's continuous, so we know that f of 1 must be 2. See, 3 minus 1 equals 2. All right. So this is going to be 3 minus x, so 3 minus 1 plus h, that's the function, that's f of that. When it's less than 1, to the left of 1. Minus 2, that's f of 1. Over h, this gets to be 3 minus 1 minus h minus 2 over h. 3 minus 1 is 2, 2 minus 2 cancels 0. So I got negative h over h, which is just negative 1. Okay, let's look at the right-hand derivative. And the right-hand derivative, the same setup, except for as h approaches 0 from the positive direction. As h approaches 0 from the positive direction, this is going to be positive, so this is going to be to the left of 1. So I'm going to use this function over here. I'm to the left of 1, greater than 1. I'm using this function here for 1. And again, I'm using 1 for f of 1. So this is greater than 1. So f of 1 plus h, when 1 plus h is greater than 1, is right over here. A x squared, this is x. So 1 plus h squared plus b times x, 1 plus h. And this is my f of 1 again, which is 2, as in the left-hand derivative. So again, there's your function, ax squared plus bx. In this case, it's f of 1 plus h, so I put 1 plus h squared. A 1 plus h squared plus b 1 plus h minus 2. Okay? So that's the right-hand derivative setup. Now we've got to work that out and simplify it. So we need another page for that. And this where it gets kind of cool now. Watch this. This is cool. So we do the right-hand derivative, and all I did was I squared that out, so that'd be 1 plus 2h plus h squared, and then I multiplied this out. Okay? So I got b, bh minus 2 over h. So that's what I got when I multiplied this out. Again, I just multiplied this out, squared this out, and multiply that b, and then bh. Okay? And then we multiply everything by a. So we get a plus 2ah plus ah squared plus b plus bh minus 2 over h. And what I'm going to do is I'm going to group my a plus b and my negative 2, because what was a plus b? Remember, a plus b was what? Way over here, if we look back over here, a plus b is 2. So what I do is I group that, so I'm going to take the, and I underline them in green, I put the a, b, and negative 2 over here. And I put everything else, the 2ah, the ah squared, and the bh, or the terms containing h, over here. But what was a plus b? We just said that that was 2. What's 2 minus 2? 0. So it goes away. So I just have this. 2ah plus ah squared plus bh over h. And the nice thing about that is, what can I do now? I can factor, because see, as long as I have this h in the bottom, I've got 0 over 0. Okay? We didn't really know what these were, but they actually happen to zero out also. But now I can factor the h out. If I cancel the h, I got 2a plus ah plus b over h. These h's cancel. So now I have, the limit as h approaches 0, 2a plus ah plus b. But as h goes to 0, this term vanishes, and I have 2a plus b. So my left-hand derivative was negative 1. My right-hand derivative was 2a plus b. In order for it to be differentiable, the left-hand derivative and the right-hand derivative have to be equal. So a 2ab must equal negative 1. Right-hand derivative must equal the left-hand derivative. So I'm going to call that equation 1, because we know a plus b equals 2. I'll call that equation 2. So now I've got two equations with two unknowns. I could solve those and find out a solution. So I'll just substitute. I could have used addition, but I'll just substitute. So we know a plus b equals 2, so b equals 2 minus a. So I'll go back to equation 1. This is the equation 2 information. I'll put that back into equation 1. So equation 1 was 2a plus b, but b is 2 minus a equals negative 1. And what's 2a minus a? That's a plus 2 minus 1. If I subtract 2 from both sides, I get a equals negative 3. So that's my solution for a. I go back to equation 2. B equals 2 minus a. That's 2 minus negative 3. A negative times a negative is a positive, so it's 2 plus 3 is 5. So b equals 5. So a equals negative 3, b equals 5. And those are the values for a and b that will make that function continuous and differentiable over its domain. Hope you follow that. That's a good one.